to use sparse categorical. Otherwise, label is represented by the hot encoding. Then what is one? Let me explain this now. Okay. Then now here, like this, you know this category is like integer 0, 1, 2, 3, k cartridge here. Category replaced by like this kind, like this integer, we have to use sparse categorical use. Sparse categorical. Now this categorical is replaced in when category is replaced by like the digit integer, then we have to use sparse category cross entropy. And like this, category is like this integer. We have to change it to one-hot encoding. One-hot encoding means category 0 means this is k bits. First one is 1, another one is all 0. Category 1 means this is category 0. 1 means second bit is 1, another one is all 0. Category 3 means the third bit is 1, all things is 0. We call this one-hot encoding. If we use y represented by one-hot encoding, we can use this kind of categorical cross entropies. Okay. One more time. Category is represented by this integer. You can use a sparse categorical. This category is represented by the one-hot encoding. We can use a categorical cross entropy. Okay. And then the entropy value that you can use in this case, n numbers of data here. This is real bar, real summation, real value, log y expected value. This is summation. This is the categorical cross entropies. Okay? And then this is one by one, this average. Okay? And then do this. Okay, now this so far, now this, then here, have some implementation, how to use sparse categorical, and the categorical one, the k equal 3, and the y represented by integer and one-hot encoding, we can use. Okay, also you can use 3 layers, first layer, second layer, third layer, and we calculate predicted value y hat and the real value. This one. Okay, let me check this one. Let me do this. Okay. Now this sparse categorical cross entropy, the category cross entropy here. For this, you have to use TensorFlow, and for floating, tensor layer. This loss as a loss, we can use a categorical and sparse categorical. For constructing the layer, we can use sequential. Okay? Now here, first n equal 2 inputs, n feature equal 3, the k equal to 3 categories. First of all, we have to use data generation for multi-class data sets. It's X inputs, and also mode means by input command we can select the output represented by the integer, otherwise one-hot. We can select here, and from this we can get the one-hot encoding means this one-hot encoding. This integer means this integer. Y is selected. Okay? And here, for making the generation, let me explain this. Now this is now n feature equal to 2 feature means we have to use now this. Now, for example, this is x1, this x2. Now 3 categories. first of all, center, you have to make a center here, center you can make. And around this, you have to make this one, this one. We have to make this. Okay. Now for this, you can use a center point here, three members here, and x1, x2, and concatenate x1 and x2. Okay, this scattering. Okay, let me do this. Let me have some here. Let me see the data sets. From this we have to select integer or 1 hot. Now I typed integer. Okay, then from this, now you can see here. Now I assigned here. Now here assigned each category, 3 category, and each category have 2 data here. Yeah, for here we made this one. 3 category. This is the center point. Around this you have to use the 3 more input here. In this case, you can use also n equal for the more data here. N equal, for example, 10 data each. And you make this also start one hard encoding. Same one. Then we can get here 3 category data we made. This one here, category 1, category 2, category 3 we make this one. By using this, we can classify. This is class 1, category 1, 2, 3 to make. Okay. And you use this one and okay. Okay. Then if this one means 1 hot encoding means that we have to make 1 hot y. This is y equal 1 hot. Okay. This 1 hot. This means okay. This means category 3. Category called 0, 1, 2 means 1 hot means 0 means 0. This is 1, 0, 0. This means 0, 1, 0. This means 0, 0, 1. Okay. This is category 2, category 1, 0. This is 1 hot encoding. I have made this one hot encoding. Y. Okay, let me see this. Okay, now. Okay, now here, let me see this one. Check here. Category is not too many. But just you have to make n equal, for simplicity, n equal just 2. You 2, then make this. Now here, 1 hot encoding. Then here, now this 1 hot encoding. This is x value 2, 3, 1. Like this, 1 hot. This is category 1. This is category 2, category 3. This is 1 hot encoding. This is y shape. Understand? Okay. Then, okay, let me comment. And also from this also we have to make dividing whole data to page size here. And the dense layer, we have to construct the dense layer, sequential, model, add, dense layer 1, first, second, third dense, we attached. Final activation function is softmax. First activation value 10H. Final should be softmax. Okay. Then mode equal 1 hot. In case 1 hot encoding, we have to use categorical cross entropy, and the category is represented by the integer. We have to use a sparse categorical cross entropy here. Now data set here. We have to in data sets calling the xy, real value, real x, and real value y, and the y hat. Okay. Okay. Let me see this. Okay. Now here, for example, integer. Then we can get here, we can get here, the real value equals 0. Okay, real value equals 0. Next one is 0, 1, 1, 2, 2 like this one. But the prediction is like this. Now this is not trained. Therefore, in this case, now let me see here. Real value equals 0, 0, 1. Therefore, now in this case, this is the most, this is the most highest one. Therefore, this is category 2 categories. Therefore, real is 0 categories, but in this case, 2 categories. Next one is 0 category. Also, next one is 2 category. And this is 1. In this case, is also 2 second category. And this is the first one. This most highest one is this highest one. 1. We can do this. Therefore, in this case, the weight and the bias is not trained. Therefore, very different, not exactly. Okay. And this is one of the process I'm showing you. Real value and predicted value like this. Okay. Okay. Then next, how to get loss for the regression models. For regression model. Okay. Now in this case, regression model here. Now so far we completed up to this. Okay. Then by using this, our purpose is how to know this weight function, weight and the bias in Europe. Therefore, loss to get minimum loss, we need to update weight and the bias. We call this backward propagation. Understand? Therefore, for the means how to get inputs to loss. Okay, how to get loss. If we know loss, we have to minimize the loss. And how to decide W and B. For this, we need back propagations. Okay? To get minimum loss, we need to update W, weight, and the bias. We call it back propagation. Okay, and for this, if we use generally, we can use gradient-based algorithms. For example, in this case, f of x equals x squared plus 5, then minimum value means x equals 0, the value equals 5 we can know. Okay? Like this, we call this gradient-based algorithms. Now how to update x function is, instead of x minus this value, and with the learning rate updating. By using this update, for the deep learning case, weight is updated by this. Bias also updated by this. Therefore, we have to know alpha learning rate is usually 0 to 1. Between this one, 0.01, 0.03, 0.05 we can use. Therefore, we have to know this one. J equal loss. Thus, minimizing the loss. Minimize the loss, how to get this one. Okay, this weight. Therefore, we have to know this one. We know this, we can update the W. Now, how do we know this? dj, dw, the round J, round B. How do you know that this? This is how do we know? This is a back propagation we can know. Understand? Okay. This is a basic concept of back propagations. Okay. The gradient-based algorithm. Gradient-based algorithm. Okay. And then we have to know this. We can update weight. If we know this, we can update bias. If we know that, that's the final course. And how do we know this? For minimizing. Equal 0 is epsilon, it is the best one. But maybe it's not the market if it's. Okay. Then from this, one of the example, in case of a linear regression, okay? In case of linear regression, here, linear regression means x and go to this one, y hat equal xw plus b. And then from this, we can get the mean square equal like this. For this, this is j, this is y. Therefore, round j, round y equal from this. Here this one, then we can get this one. Okay. Then from this, w round y hat by w equal this, we know this one equal x. Okay. And round y, this y by derivatives of p equal 1. This one. Therefore, from this we can know this one, this one. We know this one we can update. Okay. Okay. Now finally, in order for loss j to minimize, how to decide w and b? For example, this one. It is equal. This means round j, round y into round y, round j. Okay. Round j, round y means we know this one. This is this one. And the round y, round w equal x. We finish that. Now we know this one. Therefore, we know this, we can know w. We can update. Alpha equal constant. Understand? Also, this one, how do you know this one means round j, round y hat, okay, and the round y hat yb. Round y hat, this is this value, minus 2, this one, and the round y, round b equal 1. Okay, we know this. Therefore, we know this, then we can update, this one, we can update the bias. That's finished, that's all. You understand? Therefore, now, what I'm saying is how to update this weight and the bias. This weight and the bias. How to update. For this, we need this one value. We can know this. Understand? The under W is updated by this value. The B updated by this value. Okay, this is for the, let me, I suppose y hat equal xw by b. That is one. Another application or another application is for example, linear regression. In this case, y hat equal this one x square plus weight 1 plus x weight 2 plus b is here. Then from this same this the mean square. You know this round j by round y hat equal same one equal this one, and this is y, and round y the round w1 means x square. Round y w2 is x to b is equal to this one. Then we know this. Finally, we have to know this one. This one by using this we can update w1 equal here. By using this we can update w2. By using this you can update the b. This one we know this. But this one means this into this. This is we know already we know this one. That the y hat w1 equal x square. This x square. Okay. And then this is okay. We know this one, we can do that. And round j, round w2 means here round j y hat into this. Okay. And this value round y, round 2 equal x. You can add. Then we know this one, we can do updates. This one also, we can make this one. Now by using this, we can update this w1, w2, b. We can update. Okay. And also logistic regression also same concepts. Logistic regression means loss equal like this. Not like this. Therefore, first round this is j, this is y hat, therefore round the y hat. From this, we got derivative of this one equal, we can make this one. And this is y hat, this is the g. Therefore, in this case, d round y round is equal this value. And from this, dg round j dw equal, now from this equal, this is x. Round g round p equal 1. Then we know this one, this one, this one, this one. By using this, we can get round j, round w, and then round j, round w. So this one. Here, we can make. Okay. In this case, we call this logistic regression. We can use this equation. We can update weight and the bias. Okay. Okay, then for this, let me have some implementation. Data set equal this one, this value. Okay, when weight W1, W2, and the B in the plot data set. Okay, let me do this. Okay, let's have a regression method. Here, this is a real value. X square, W1x square, Wx2. And from this, the n equal 500. X learning rate equal, I said 0.001. The target weight is 1, -2, 3. And this is target. For the initial, we have to W1, W2, we have to train, and we can do that. What this value goes to 1, -2, 3. For this, generating data set, random data, and y data. Okay. And here, okay. And for this, visualize the data set. Let me see this. Okay, let me see this. Now this is data here. Y square data equal like this one. This is here y data. Sometime, okay, like this it is. Okay. Then how to make the training? Make the training this one. Weight vectors. Weight vector. We have to update this W1, W2. For this, we can do is tracking losses here. List W1, W2 list we can make here, and training. For this, track we can use W1 track appending, and for the propagation anyway, x2 x square W1 plus x W2 plus p. This is first y hat prediction, and the mean square error. This is mean square y minus y hat square equal this is error loss. Okay, mean square error. Then we can know the error. Then next we have to use update W1, like this one. Already I explained here. Okay, now here where is this one? Not this. Now this. Not this one. Not this one, I'm sorry. Okay, anyway, just before I explained, update W1, W2, be like this. Then let me see the one. Okay. Now, okay, this is a 16 accepted. Now this you have to comment here. Okay, that's it. Okay, now here, the weight target is 1, -2, 4 is 1. Red is 1 is, so this one, for the iteration is going to here, almost the convergence here. This is 1. And another green is also, target is -2. First is not working, but epoch times go to here. Many times we use many data, we can get about here. We have to use 300 data. We can make this one -2, 1, 3 converge here. Like this conversion. Understand? That what I said is by using this data use and update this here, updating this one. By using this, we can get the final target one. We can get here. Final target is 2. Okay, final 2. Okay, now this one 1 -3 target you can get here. Okay, this is the application of this is the back propagation. By back propagation, and with the update weights, and then we can get this. Okay? First, that is very different one, but the real vehicle one, different one, and go to here. About we use 300 data, almost you can get 1, and this is 3 and -2 we can get here. Okay, this is the one. You understand? Okay, one more time. What I'm saying is, okay. What I'm saying is, that programming we know that this one loss. From this, we need to minimize the loss. For this, how to know this W? This one W. For this, we need back propagations. For back propagation, this is gradient-based algorithms. Okay, that is one. That of X. Okay, now here, in this case, X is updated by this one. This is gradient-based algorithm, gradient descendant, and rates of updating. For example, in case of in deep learning, weight is updated by this one. That we have to this one. Bias also rated by this one. That we have to calculate this one. dj dw. Okay, this loss to minimizing the loss. How to get this one? Also, round J by round speed. So, same one. Okay. For this, for minimize effects, you can use the derivatives of this one. This is basic concept of this. Okay. And for this, in case of linear regression case. Okay. Now here, this is X. This is Y, this is Y is X to P, and mean square equal this one. Okay. Now from this round J round Y equal we can take the derivatives with respect to this we can get here, and also this is Y to round Y round W equal X, round Y round B equal 1. We use this one. Yeah, fine. We want to know this one. But we can use a chain rule. Okay, chain rule. Okay, okay. Now this means this round J round Y into round Y round J. Then we know this. This is this value. This is this value X. Then we can get know this. We know this, we can update W. Okay. And also, round J, round B means we want to know this one, we want to know this also, chain rule, round J, round Y hat, round Y hat. Round J, Y hat means this value. Round Y hat equal 1. Then finally we can get this. Therefore, we know this, then we can update by using this. Okay, this is the one. This is the, I have explained here. I have explained this one. W1, W2, B is updated by learning rate 2 into something, this one. Okay? Same one. This equation I explained here. Okay. Update. Here, let me check this one more time. Now this is the real value, and like this, target is 3, 1, minus 2. This is a tracking of weight, and the bias is go to the this one. First, it's not good, but if we use many data here, we can get the final accurate value. You can know that. Otherwise, also you can do this y. This is the real value. Also here y real value. You have to we can add some noise. It is some noise here. The noise here. Okay. Let me do this one. And y like this. This noise is added here. Then in this case, also. It's a processor here, and we can get the minus 2, 1, you can get here. This is a loss function, that is mean square. Sometimes mean square is finally mean square is almost zero like this one. Almost zero. Mean square error zero means the same meaning. Targets, and the desired weights to be same one. Okay. Okay, then next. One more time. Back propagation means we have to know weight and bias to minimizing the loss. Then we have to iteration this one. We have to make updated WMP by using back propagation. Then, in case of this classification problems, 2 layers. Okay, this is a little bit complicated. Okay, now here 2 layers means this is 1 layer. Okay, this is 1 layer. This is 1 layer. Okay, 1 layer. Now finally, you can get the loss here. Therefore, this is a loss in the y hat. Therefore, dj dy hat equal like this one. Okay, and because the j equal loss equal, this is loss. But this is a loss. This is a categorical loss here. And loss here. We can move it. Okay, this is equal J. Now here, dj dy hat equal this is minus 1 by 1. This is constant, and this is yi the constant y, and this is lower equal 1 by hat. This means minus n by 1 y by y hat. Okay, this is dj dy. Okay, like this. Okay. Okay. Now this dj dl equal, we can get this one 30%. Yeah, this one, and the next dj dwt. This means first of all dj dl into dl dwt. Okay. Then from the dj dw equal, this means dj around j around l means this value, JL, and round SW means this is L, derivative by W2 means just A1 comes here. We define this JW2. Okay. And round J, and B2 means round J DL into this. Round J, round L means JL. Okay, JL, round J, and round L, round B means we can use this one. Summation over JL. And also here, in this case, round J, round A1. For this is round JY into this one. Now in this case, round J, round Y, round J, round Y, round Y. This is the round J, round Y. Okay, round J equal JL. This is the JL. This is JL, and L round by 1, which this is A equal L. Okay, L. Now here L round A1 equals W2 is here. W2. Okay, like this we can get here. From this we can get here round J W2, round J B2. Round J W1 can do this. So this one, we can get the classification questions. Okay. For this, categorically here. Now also 3 layers also you can make same concept. This is first layer, second layer. This is the 3 layers. The same concept you can get this value round J round W3 B3 from this round W2 B2 W1 B1. So you can get 1 2 3 4 5 6 parameters you can update. Okay. And for this, let me make some example. Then here we can update. Just I said W is updated by this value, and the bias is also this value. Okay, for this W3 P3 updated, W2 updated, W updated. Learning rate is 0 to 1. Usually we can use this. Okay, for this, here let me explain the data set. Whole data set is here. We have to divide by 3. One is a training data set we need, and another one is validation data and the test data here. By using the training data, we have to make learning the data models, building the model. If we use a model, but the neural, this is dense layer, we can use that. Then from this, we can model test. Okay, model test. And then finally, by using this, we can get building the final neural network models. For example, how many numbers of hidden layer, and then numbers of neurons. What kind of activation functions? Sometimes 10H equal good, sometimes sigmoid is good, sometimes L is good. You have to make this one. And then finally, by this test data, we have to evaluate neural model here. That this is good or not. Therefore, you have to use, definitely, you have to divide the trained data and the test data. By trained data, you have to construct model. And then this model is good or not, you have to evaluate by using the test data, not this one. Okay? And also, now I said Now here we use for the epoch batch size it is used here. For example, total data is like 1000 data here. Usually we don't use it together. We divide by this size. For example, we call it batch size. Then this batch size like this one. Okay, this is batch size 100. Then the whole data we call this epoch 1. The epoch 2 epoch equal 20 means 1000 we can use 20 times you can use. Also one epoch is divided by batch size. Okay? Therefore the epoch means whole data. Batch size is whole data is divided by some numbers. For example, usually you can use 34, 128 like this one, 256, 2 to the power of p you can use. Anyway, 100, 200 is no problem, you can use. Okay? Therefore, now this is the terminology epoch and the batch size. Okay, then now let me have some data sets. Let me introduce handwritten 10-digit like this one. Like this is for training data is 55,000 samples. For test 10,000 samples here. By using this, let's implement. Let me implement this one. Okay. For this, you get here. Now load data set from test flow, training data set, and test data set. Training data set is for network construction, and this is evaluation of network. Okay, and visualize 15 samples, and assign hyperparameter. Just the 2 layers. First layer is what the input is here. First layer is 128 neurons. First next is 10 categories. K equal 10 is 10 numbers here. This is 10 to 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, and 9. Okay. This is output. Here you can have therefore we have to use softness. For this we can use categorical cross entropy. Okay. Let me see this. Let me explain the code. Okay. For this, we need also TensorFlow, and the numpy we need, and the 4 random numbers, normal, and the zeros for plotting this one, the 4 data rows for data set, row data, this one. Then first, for raw data, we can get training images, training labels, test images, test labels. Okay? Let's train the printout and visualize this one. 15 figure, plotting figure, figure size equal 15 by 10, and also plot. This part 10 means this total figure equal 50 means this is 5. This is 1, 2, 3, 4, 5, and 10. 2, 3, 4, 5. 10. Then total we can get 50. That's 5 into 10 equal 50 is an images here. So to show, okay. Okay, let me see this one. Well, without remove comment and okay, stop down. Okay. First of all, downloading data from this site. Okay, you could just end list. From this, we can know training image size is training data is 60,000 and 28. Therefore, the image size is this means 28. This kind is 60. For training 60 images here. Okay, and the label also this is 1, 2, 3, and then for set data also 10,000 data, the same size 28 here. Okay, Then here, you can see here this one. For example, 5, this is the red is a label. Label, this is label means answer. Okay? 5, 0, this one, this kind. This kind of it is 60,000 samples for training, and for tester 10,000 samples here. This is the one example. Okay? Okay, let me comment here. Okay. Then next, assign hyperparameter means the number of data n equals 60,000. And feature means this image is 2828. Therefore, 2828 equals 784 is n feature size. The batch size equals 64. 64 means, just before I said, total number is, this is 60 images here, okay? This is images. From this, we can make this 64, 64, 64, like this. Batch size means. Okay? And then from this, we can get n batch. How many batches here? Then from this, we can get a flow division. We can get here. So, and epoch means 20 means 60,000 data we have to use 20 times. The total we can use the data is 60 into 12 data. Therefore, 72. This one, okay, data. Now here, learning rate equals 0.03. In the K equals 3, 10 means category 10. 0, 1, 2, 3, 4, 5, 6, 7, and 9. Okay? The unit distribution means the neurons number. First, the neuron number is, the number of first layer is 128, and the next is 10 numbers. Here, first our 2 layers, W1, W2, W2, 2 layers here. Okay? This means, you know this, do you explain? Okay. Now, X equal 1, now this 28 into 28 equals 760. First layer is, I said here, neuron is 128. This is 128 neurons. 128 neurons. Okay, therefore, we have to use this one. For this, we can use W1 and the bias one is here. Next is 10 neurons here, because K equals category equals 10. Then we can do all this one, also you can use weight vector, bias vector to teach here. Therefore, we can use W1, B1, W2, B2 we have to use. Therefore, W1, initializing W1, B1, W2, B2. Okay? And here, just let me see the shape. Here. Now this is W1 means X equal 706 data here, and weight should be this into this one. Okay? Then 702 into the bias equal same one. And also next day is, this is input and output is 10. Therefore next day is this first layer, next layer 102 into 2. This one 102, 2. Then we can get output here. 10 number output comes. Okay. Okay, this one. Then next, initializing and forwarding in the back propagation with this. For this, we can start the index batch size here, and then we can you can call the image data and start. We have to use batch size numbers. Now batch size equals 64 numbers here. Okay, Now up to this, okay. And now this is two dimension that we have to make a two dimension to one dimension to make. What do we have to make? Immediately reshape. Two dimension to one dimension reshape. And the y dimension, this is real value. Therefore, x, y we know. Okay, from this, okay, now we see. Okay, now we see this one. Let me see this. Now this x shape is 64. Now, okay, now this x equal one image. I said one image is equal 28 to 28 because this is 1,784 is here. And this number 74 is here, 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 here. The total is 64 numbers. Therefore, 64 into 782 is here. This is x is here. Then y equal 1 by 1. This is 1 into this label. This is 1, 3, 5, 7, 2, 3, 2 like this one. This is 64 numbers here. Understand? This is x. This is y like this one. Okay. Okay, now this, okay, now this, okay. Now this comment, and this also comment. And for the progression, this x, this is a matrix multiplication, x w1 plus b1. This is L2 the prime function, and this go to here activation function. Here is your sigmoid function. Okay, this one. First layer. This first layer. One output is here. The prime function is xw1 plus b1. And this is activation sigma g equal to g. Sigma g. This is activation function. And the second layer also this A1 input, then A1 input and the WT and then P2. Okay. Then next we need to we have to change softmax. Softmax, okay. Softmax is, as I said here, softmax means output from this y head is y1, y2 head go to y 0 to 9 head. From this, we change probability P1, P2, P3. For this, we can use this. Okay, this is y hat. This is y hat. And sum. And next, what you have to do is, and from this, we can get categorical cross entropy by using this categorical entropy and this average. Okay, and loss. Then next, we need to calculate the accuracy. Means y means y label is y hat. Now this y hat equals this one. For example, y1 hat equal 0.1, y1 hat equal 0.001, that is y9 hat equal 0.5. For example, from this highest one, you can take highest one. Okay? Highest one. or maximum factor, we can get this one. This is 9. And correct means this value, this real value is the same, then you can get correct. Otherwise, it's wrong. Correct means the same. This real value, the predicted value is the same on this one. Then the bit size. Okay. Then next we can propagation, back propagation. For this, we can use the label and one-hot encoding from this one-hot encoding, and then we have to calculate the loss by using this. Okay. Now minus 1 by this one from this JW1, JW2. Okay, now you see. Okay, let me see this. Now this. Now this. From this we can take, we can calculate this value, this value. By using this, we can get this, all this one. Okay. Then here, same one. Loss. Dense layer here. Then we know this one. From this we update W2 equal W2 by learning rate JW2. You have to read this one. Okay. Okay, let me check. Now, for example, okay, that's this one. Okay, execute. Then for this it will take some 1 minute because there are so many data. Okay, the training data is 60,000, and then we have to repeat it 20 times. Okay, for this forward propagation and the back propagation we can do. Now it's 17 around, I think 1 minute it will take. Okay, this backward propagation here, forward propagation G1, A1, and the last dense layer here. And from this we can get the softmax y hat, the predicted value, and from this we can get the loss, the category cross entropy here, and then we know the loss. Then for this we need to back propagation is here from this. Okay, now this. Okay, now for training data, the accuracy is around 86% like this. Okay. Then now up to this, we have to use W2, B2, WB1 we did one. By using okay, now this visualize this accuracy here. Okay, let me see. Now here, loss function, category cross entropy. First, this is a very large one, but go to here, very small, so it goes here. Almost 0. And accuracy is equal to first, there's around 30%, then it goes to around 67%. Goes here. 87%. Then so far, we know we obtained W1, B2, we know this one. Then by using this, we can classify the test data. Classification for test data, okay? Then here, we have to use the test data images, and then reshape to the here, label, and then go to the forward operation, propagation here, and the y hat is here. Then the y hat, and this is y hat label, and the true value is the same one. Then correct equal, and on correct is will be increased by 1. Okay. Then here, it's no time because already we know this one. So we don't just already we know W1, W2. Not this we know this one. It does not take around 86%. Okay. Now this, I think so many data, 6,000 data, 10,000 data. I using this just we use the 2 layers. One, just we use first layer, just 2 layers. Even though just with 2 layers, we can use almost 60%, 86% we can get. It's incredible, I think. Understand? Okay. Now here, as I shared, I displayed the source paragraph here. You can hear the 3 layers here. You can do the please. Now, just I have explained in case of the 2 layers here. In case of 2 layers, I did. Even though 2 layers, we can get more than 60, I don't know, 86% for the 60,000 handwritten data. It's incredible, I think. Before this, we do the pattern matching, image processing, we cannot get more than 60%. Maximum 60% you can get. But now, since we use 2 layers, we can get. Even though we use 2 layers, we can get more than 86%. And you can try more. Okay. Okay, let me say this. Okay. So far, I have explained this concept. Okay. Input, dense layer, sigmoid, or softmax for decision. Now, in case of regression, there's no need of this one. In classification, we can use sigmoid or softmax. Okay. Then class K equal 2, we can use sigmoid. K equal more than 2, we can use softmax. Then we can get here loss. Loss means also we can use the mean square error. This is a regression method. The binary cross entropy, sparse categorical cross entropy, categorical cross entropy you can use. Mostly you can use 4 kinds. You can select. Then by using this, then the purpose is W and B. For this, we can get round J, round W, round J, round B like this. For this, you can use chain rule. You can get this one. Okay, I'll explain. That's all. Very simple one. Okay, vertical here to here. For the propagation, we know for minimizing the loss, we can get the weight and the bias by using the derivative of this. This is a gradient based algorithm.